Okay. So many buttons to push. Okay, so let's go ahead and pick up where we left off, right? So we got really far, right? The first slide was impressive progress. So what we wanted to do, remember I said that in this particular chapter, chapter 1, we're going to be working on starting conversations that will carry throughout the semester. We'll be talking about some foundational ideas that we will build upon. And so there's a combination of things that we're going to be covering in the first chapter. We'll kind of use that to kind of weave our tapestry, right? Our tapestry of biology. I use that analogy. And so before you weave a good tapestry, you got to sit down first of all, and you have to analyze what kind of thread you have. It was very loud. It's very clear. So it's very, that's a good thing. That means it's all working, right? For your device. So we want to kind of start talking about some of those threads now as they kind of start to weave throughout the semester. There's several of them. So the first one, obviously, is going to be evolution, right? And that's kind of going to be a big one. I left you guys with the famous Dawkins quote, right? And I modified it. I had the gumption to modify. Check your guys' mics. Is it that one? Okay. Mariana's all like, it's not me. I promise. Okay. Okay. So basically, when we take a look at that, I had the gumption to modify that, right? And I'll explain why that is actually more accurate because, and I also warned you ahead of time that I'm a bit of a history buff, right? I study value in going back and learning from the mistakes that we made so that we don't make them again and again and again and again and again, right? And so a couple of things, first of all, and I want to spend a little bit of time in this chapter talking about something that, to be quite honest with you, is kind of ironic. It's that you don't really talk about it a whole lot in a biology class, which is kind of why. So that little tag up there stays there until I actually push the button. So that means they jumped on and popped off. And it's like a bad Wi-Fi connection, right? So, so here's, we kind of lay the groundwork. Remember, we kind of started talking about this a little bit, right? The idea of kind of where we were at the particular time when Darwin went on his famous voyage on the HMS Beagle, right? And we talked a little bit about the idea of a natural historian was sort of a career choice that you had. Now, let's see if I can run up there and get it this time. And so this was kind of like what we now refer to as a zoologist. That's kind of what a natural historian became. They basically studied nature. That's what they did. I mentioned a couple of them, right? John Muir was one. He focused more on the West, California, things like that. Darwin certainly the biggest of them all, right? And so his job basically was to, like any natural historian, was to collect organisms. That's basically what they did. And then you guys come in. And then make sense of it all. So what he basically did, like everybody else, was he went on this voyage, and the Beagle was a British thing, right? So that was, you know, they were exploring. That was kind of like early Victorian. Actually, I think I looked this up. It actually wasn't quite Victoria just yet. I think there was somebody in there, an Edward or something like that. But Victoria was dominated the 19th century, right? She kind of created the sort of the British Commonwealth. And so the Beagle was kind of like that preliminary sort of adventure across the world for Britain, probably like a kind of an ambassadorial type of a sort of a thing, basically making connections, setting up trade routes, right, negotiating different sorts of things like that with different political entities across the world. And of course, on that ship, they had their natural historian, Darwin. Right? So while some of the others were busy wheeling and dealing and talking politics and trade and economics and stuff like that, Darwin's job was to basically get out there and collect animals, which they did a lot of, and Darwin did a lot of, and he basically collected a ton of stuff. We typically oftentimes dwell on Darwin's work on the Galapagos Islands, which he didn't just go to the Galapagos, he went all over the world, right? So by the time he got to the Galapagos, which is kind of toward the end of his journey, or end-ish of his journey, it took a few years to do this, he had a ton of stuff on board, right? So there's a lot of stuff that he had. Natural historians, typically, they drew stuff, they sketched animals, they were oftentimes artistic. That was kind of part of the job skills, like Audubon, right? I mean, Audubon's drawings are famous. We still have calendars of the birds that Audubon drew. And the reason why they had to draw them is because over a ship voyage of several years, those bodies don't preserve, and you certainly can't bring them on live, right? So it's not a zoo ship. So you had to kill them and bring them back, right? And unless you had a taxidermist on your ship, then you were stuck with having to draw it and sketch it out and stuff like that. And so Darwin did this, and basically he got a really loud and clear message across the world. There's a lot of stuff out there. I mean, there's a lot of stuff out there. And the reason why this is important is because this concept of natural historians going out and collecting animals and critters and specimens and things like that was kind of like the first time where, as sort of a global personage, I guess, people were actually systematically going out and attempting to sample and discover what was out there, right? That was kind of the first time we started doing that. What we realized was basically there's so much stuff out there, it kind of blows our mind, right? There's all kinds of stuff. The loud and clear idea there was life is very diverse, right? So there's a lot of different things out there, a lot of different looking things, a lot of things out there we just don't understand. We don't even know what they are, right? And so what Darwin did then, as he came back home, is he had all this stuff. And of course, the natural thing to do is to basically make sense out of it all, right? That's what you do when you collect a bunch of raw data, is you sit down with statistics and you try to organize it, and you try to make sense out of it all, right? And so that's kind of what he did. So he basically had all this stuff and he's trying to make sense of it all. And the important thing about what Darwin was doing was he wanted to understand how all this stuff is related, right? That's a common sort of a standpoint that we have, is how are these things related to each other? And so what he started to do was something that we kind of naturally do. He started categorizing things, right? So it's like, well, I don't even know what this is, but it's kind of a dog-like thing. And so I'm going to put all the dog-like things over in this pile, and all the cat-like things over in this pile, all the bear-like things over in this pile. And then we'll kind of first start to organize them that way before you actually start getting into each individual pile and start taking a look at them and their differences and things of that nature. And so that's kind of what he did. That's a lot of what natural historians did. Basically get out there, understand what's out there, and then try to understand how they're related to each other. And it's kind of like, it's kind of like the way we deal with ourselves, right? I mean, we organize and sort of sort ourselves out as a people group. Culturally, we kind of have similarities to each other, differences between two different cultures, right? So we kind of sort of separate and organize ourselves, although not intentionally necessarily, in kind of the same way. And that's kind of what we did with the animals, was basically say, well, these guys are more closely related. And we did actually use our own personal relations as well as a way to understand this. So the idea is this: I am much more similar to my siblings than I am to you guys, right? But I'm much more similar to other members of, say, a common culture that I happen to exist in than I am to someone from a completely different culture, right? So that is to say that you're kind of grouped together, and the more closer you are to your grouping, the more similar you are. and that extends to relation, right? So for instance, I'm obviously related to my family, but I'm also kind of distantly related to the ethnic and cultural group that my family comes from, right? Which is somewhere in Europe, right? So I'm more related or more closely related to, say, for instance, the Europeans than I am, say, for instance, somebody from South America, right? And so you have this kind of sense of the similarity of organisms being a reflection of how closely they're related to each other. And so we kind of use that concept and that conception as we're sort of starting to sort through all these organisms and try to figure out how they're all related to each other. And so that's basically what Darwin was doing for a good chunk of his career. And then eventually what all those studies led him to was the development of the concept of evolution. And as it kind of equates to this diversity, right? So the big question is, where does diversity come from, right? How does it get here? How do we get to be this diverse? That's his question he's answering. And then the paper that he wrote, which was actually titled On the Transmutation of Species by Natural Selection. That's the actual title of his paper. And he published that in 1859. That was basically proposing that natural selection was one of the ways that you actually got species to change. Now, here's the one thing I want you to key in on. That's the so-called evolution paper, right? That's the paper that everybody kind of looks back at and they're like, okay, so that's kind of when evolution began. That's actually not really quite that accurate. There were already pieces of the concepts of evolution already in place and kind of rattling around. They just weren't really kind of gelled together until this kind of paper started to kind of pull stuff together. But now take a look, and a lot of people ignore this, right? They key in on natural selection and they just want to go right after that. But notice what he starts off with. He's talking about the transmutation of species. Now that's kind of a fancy 19th century word for basically change, right? Basically you could rephrase that title as, how do species change over time as a function of natural selection? Okay. Now here's the thing. How does a species change? Well, we're going to learn about this, right? Because I talk about it a lot. The only way a species can change is by changing the information that basically creates the species, right? In this case, DNA. So if you change your DNA, you change the species. That's the only way a species can change. So what that means is the entire concept of evolution at its heart is driven by genetics, because that's the only way a species can change. Okay. So that's the reason why I had the bravery to alter the great Dawkins quote and say that he was almost right. Right? Because the epicenter of biology is not evolution. The epicenter of biology is genetics. And actually the epicenter of all life is genetics. And I'm going to explain that as we move forward. Now, one thing that I also want to come clean with is I am biased, certainly, because I'm a genetics person. And so I see the world as a function of genetics. I happen to think I'm right, but I'm willing to explain and to try to persuade why I believe I'm right. Okay. And that from genetics flows everything else. It's kind of like that, it's that one thread that if you pull on it, the whole tapestry comes apart, right? So, but here's the problem, because we're not done with this slide yet. We're only just beginning. This is like the slide that never ends. Why? Because Dawkins was right. I mean, evolution is important. It does actually pull together not just biology, but actually evolution is a really, really, really big idea. There's a lot of different disciplines that are involved in evolution, not just biology. So there's a lot of facets to it. It's a very complex concept of life and the history of the earth, right? It's not just life, it's also the history of the earth as well. And it involves many different things from many different disciplines that look like they have nothing to do with each other, but in reality, they're all sewed together by this. And so one of the things that I like to do, because a lot of times you don't really actually hear anybody teach evolution unless you take an evolution class, or an ecology class or something like that. This is a place to do it, right? Because if it's true that evolution is a very important concept of biology, then it ought to have a bit of go over in a biology class like this. Okay. So ultimately, the thing that I always kind of fight against, remember I always said I'm not afraid to poke the bear. The one thing that drives me the craziest is the way evolution is taught. Most people get kind of an Elmo Sesame Street level sock puppet version of evolution. They get half-baked concepts and ideas that have been stripped of all of their complexity into something so simple that it's actually deceitful. And that's the way the general public is educated when it comes to evolution. We've all seen the National Geographic shows, yes? I love to pick on National Geographic because I love National Geographic and I love to pick on it, right? There's me poking the bear, right? National Geographic's a lot bigger than I am, but I don't care. I'll still poke at it, right? So we've all seen like these big shows where they kind of talk about like, you know, like a dinosaur show, or maybe a show where they're talking about the Triassic or something of that nature. And they're kind of like sort of painting a picture of sort of this is what life was like in the Triassic. Here you've got your cycads, and this is what T-Rex looked like and did, and how all these interactions are, and all of that. But here's the problem. They kind of give you a simplified statement of this is how it is. But in reality, it's not that simple. Typically what they do is they paint a pretty picture so that you can understand what's going on. But in doing that, they kind of don't really communicate very well that, well, that's one possibility of how it could have been back then. But the problem is, it was so long ago that it's difficult to really get a clear conception of exactly how things were. We have hints, right? And we have teases. But to say that this is what color T-Rex was is a little bit of a reach because we have no such data. What we have are hypothesizing of what we think it could have looked like. But typically when we do that, and you see this in National Geographic shows, you see this in any show, you see this in museums, you see this everywhere. They create a picture, like the artist rendition of what the Triassic or the Jurassic looked like. But they don't ever bother to tell you, as just the lay public, that this is only one of maybe a half dozen potential scenarios that we think could have been. And we can't really tease apart which one is because we don't have data because it's been gone, right, for a long period of time. And we don't have actual data that says, aha, this is the color of T-Rex. We don't have a piece of T-Rex skin where we can actually see this is what the color is, right? And the reason why we know that is because for the longest time, we assumed for no reason whatsoever, based on no data, that all the dinosaurs were cold-blooded, right? They were lizards after all. They were reptiles, weren't they? They're all cold-blooded, as are the reptiles of today. That is not a conclusion. That is a hypothesis. That is a spitball idea that you think might be, but there's no evidence or data to support it, right? It's a claim without a premise, which makes it logically fallacious, and it makes it a non sequitur, which is an inappropriate logical conclusion, right? Your conclusion does not support it by your premise. And the reason why I use that example is because now, over time, we have sort of slowly changed our perception of the cold-blooded lizard to now more of a warm-blooded animal. And there's like, we started thinking, it's like, well, no, actually, I think these guys are warm-blooded. Why? Because of the way they move and the way they run. They have to have a high metabolism. They can't just sit there and bake in the sun forever because we've got things chasing other stuff around. And so they have to have a warm-blooded strategy in order to be able to support that. So now we think they're warm-blooded. But here's the problem. That's just a hypothesis in the other direction. You still don't have any data to prove that these guys were either cold-blooded or warm-blooded. And so you can see the problem there, right? Because all the direct evidence that would have given us the ability to determine that once and for all has all long since been destroyed through eons of Earth history. And all we've got left are chintzy little pieces of ragged fossil. And they're pretty underwhelming. And so that's kind of the problem, right? There's a lot of complexity there. And this is, by the way, true for all science, right? In every scientific conception, there are a group of ideas. Typically, when we present it to the public, we present it as one front. We know this. That's kind of what we do, right? That's not actually true. In science, there are variations of quality of knowledge, right? So for instance, there's some things that we know pretty well, and we're pretty confident about these, right? So we're not really questioning this. We got a lot of data and a lot of supporting evidence that suggests that this is actually consistent with the way we think things are. And those are very strong. I'm thinking of things like cell theory in biology, atomic theory in chemistry, things like that. Right? Things that are just like, yeah, we're pretty comfortable with this one. We're not worried about this one. And then there's some on the opposite extreme where it's like, if I'm honest, I don't really know. Right? I think I can spin some yarn. I can produce some ideas, some theories, some explanations that could be, but we don't really have a lot of direct evidence for that. And so I don't really know one way or the other, right? So usually what you see in that area is you see a lot of competing ideas, variations of how it could have been, right? And then in the middle, you kind of got different ideas that are somewhere in between, right? Some that are strong because we have a little bit of direct evidence that suggests they're consistent with our ideas. Some that are a little weaker than others because we don't have a lot of direct evidence. And so there's kind of a variation, a sliding scale of how well do we know something. You never get that message in any of the public-facing communications from any scientific source, right? They're all over here. We know this, right? The one thing I hate the most, absolutely the most, is the term, and it's a COVID, it kind of came from COVID, right? Science fact. You heard that one? I hate that term because science backs away from absolutes because they always leave the door open to basically say, you know, just because we don't understand it doesn't mean that there isn't, you know, that there's something we haven't considered. There could be something, even with the atomic theory, nobody questions that one, or gravitation or something like that. There could be something that we don't even know exists or that we don't understand because we are limited where we are currently. And maybe sometime in the future, we'll have technologies will open that up for us and we'll realize, oh, warp core theory is a thing, right? Right now, it's nothing. Sorry, truck fans, it doesn't exist, right? But that's kind of the idea. And every scientific concept has that spectrum in them, including evolution. And we do a pretty good job as a science community communicating that in most ideas. But when it comes to evolution, it gets a little dysfunctional. And we do a horrible job of actually communicating that sort of sliding scale of confidence in our ideas to the general public. Okay. Another bad one is medicine, right? We don't do a very good job there either. We only do that when we're forced to by the government to say, let's say, oh yeah, this will save your life, but it can also kill you, right? So here's all your side effects. You know, most of these are catastrophic. So it's like a coin toss. So it could save you or it could kill you, right? So we don't like to lead with the "it could kill you" thing. We always like to say, "It's just going to save you," right? And we try not to talk about the rest of it. And so medicine is kind of a little dysfunctional that way too. In evolution, basically, this is the way it was. And then we don't actually talk about, yeah, but there's alternate versions of this story that could have actually been viable as well. We just don't know. And with evolution, the hard part with this one is it's got the time scale to it, right? So when we're doing species change in near term time, and what I'm talking about is like maybe family level back, tens of thousands of years, hundreds of thousands of years, something like that. It's a little easier to understand, right? Because we're closer to that in history and in time. When you're talking about things that are way, way back there, like cell evolution, 3.5 some odd billion years ago, I mean, it's nearly impossible to really know for certain exactly how it all came together. Because all the direct evidence for that is long since been expunged from the face of the planet. And so all we really have is kind of what we have now, and we can kind of extrapolate back or sort of hypothesize and theorize like, well, how did this come to be? Well, maybe if it kind of did this and this and this, and maybe then we could lead it, but then we could do it differently over here and over here and over here, and all of those could have led to us, right? So we just don't know which one of those is. So the further back we go, the less certain we are of how things are. The problem is in most scientific endeavors, you see that language shift. You see people saying like, yeah, the more uncertain we are, we're pretty uncertain. It's good so far, but we're hedging our bets, right? So we need to do a lot more work to make sure we're feeling confident with this one. But for some reason in evolution, like they talk about things that happened 3 billion years ago as if they happened yesterday, and they had photos of it, they took pictures of it, and it's all there. When most of it actually, they have very, very little data, direct data, to actually lead. It's more hypothesis. It's a good one. I'm not saying it's bad. It's a good one, but it's not actual science fact, right? That just drives me nuts, right? Because that's a little too absolute. So here's the thing, and here's the problem, because what I want to do is I want to try and sort of demystify the dysfunction of evolution. And in science, we are partly to blame in this dysfunction. Okay, there's plenty of blame to go around. It takes two to tango here. But here's the problem. So here we have a scientific concept of species change over time. That's evolution, right? Darwin also recognized straight off in his title that this species change was a function of genetics. So now we have two very powerful concepts in biology set up here for us in evolution and genetics. Now, the rational, reasonable mind would basically get to work on understanding both genetics and also how that leads to species change, right? That's what you would basically be doing. And you would think, well, is that what happened? Unfortunately, the answer is no. What happened was nearly 100 years or more of powerful scientific dysfunction, and just cultural dysfunction in general. Because here's what happens. Instead of scientists leveraging all of the beautiful attributes of science in order to solve problems, difficult problems, like our methodology, we'll talk about that later in the chapter as well, and our mindset, the way we think about difficult problems, instead of leveraging that to try to get a discrete, objective understanding of how this stuff is working, what ended up happening instead was the concept of evolution got picked up by a bunch of theologians on both sides of the theological fence, the theists and the atheists. And basically what happened after that was more essentially a battle between those two groups for a couple, like 100 years at least, of them going back and forth and back and forth. Where the atheists had the aha, and they said, aha, here's a mechanism now that omits the concept of deity and a creator of the universe and all that sort of stuff. And so we're going to basically use that as a new weapon in our age-old battle against the theists, right? And by the way, if you're wondering, and this is just the philosophy aside, that debate was not new. that debate between atheists and theists has been going on for millennia, literally millennia. The Romans beat each other up over this one as well, right? There were atheist or agnostic Romans who did not believe in the concept of a deity. And then there were others that did. They were arguing more over the Roman gods and stuff like that. But, you know, every culture has this debate. It has been with humanity since the beginning of time. It will be with us until the end of time. This was just a new iteration, a new version of that age-old debate. And since then, the reason why I mentioned that is because that right there is what created the dysfunction of all of this. Is because you were using something from one intellectual discipline to argue inappropriately, I would say, a conclusion from a different intellectual discipline. So in a sense, they were abusing and misusing science for their own agenda. You know, so you had one side basically using evolution to beat up and say, see, this is proof deity doesn't exist. And the other side, whose response was to vilify and demonize science. So now all science is bad. And none of those two groups were appropriate in that approach, because all anybody really did as soon as you talked about evolution was just, you know, if you were a theist, you couldn't even think about science because you were thinking that this was bad and evil, and that was inappropriate. And that lasted for like a good 100 years. So it basically paralyzed anybody from being able to actually make good, sound, objective headway on what Darwin laid out. Okay. And that was unfortunate. The other part that added to the dysfunction, only just a little bit less so, is the fact that we didn't know anything about genetics. Darwin tried, failed. Right? We didn't actually, the father of genetics, Mendel, didn't come along for another 10 years or so. And so that didn't come until after. And not only that, but the level of genetic knowledge we have didn't come around for another 100 years. So we are just now at a point genetically where I think we're about where we can start to take a look at how this all works out from a genetic standpoint. So in the absence of genetics, what did you use? Fossils. This is the age of paleontology, which, to be quite honest with you, I'm not a fan of fossils. It's basically, I call it the rock zoo. Fossils to me, I mean, I know there's paleontologists who swear that they can solve the problems of the universe by looking at a fossil. I almost always roll my eyes and balk at that concept, because all the fossils are no different than the animals that we already have. You can't solve the problems of the universe with the animals, the diversity that we already have living on this planet. You're not going to do it with the fossils. The only difference between those two is one is dead and the other one's not. One group of animals is extinct, the other one is not. So, especially when you're taking a look at the real evolution, if you want to understand how things change, fossils aren't going to tell you. Because fundamentally, all a fossil tells you is, I'm either here or I'm not, right? I mean, that's being a little cynical, obviously, but that's because my inner geneticist is kind of rolling his eyes at fossils. If you want to know how an organism changes, guess what you need to understand? Genetics. Because that is the only way that an organism changes, including the organisms represented in our fossil record. So just by digging out a fossil doesn't really convince me that you have any greater awareness of the relationships than we did before discovering the fossil. Because the change in the relationships between organisms is a genetic thing. And unless you can lay down the genome of T-Rex and do a cross comparison with T-Rex and the other dinosaurs and do a genomic version of their relationships, that's where we want to go, right? And for the first time in history, this is basically where we are now. So we are basically in need of transforming evolution a little bit, reimagining it, kind of putting away the fossils and sort of redefining evolution from a genetic standpoint. And that's where we're going to really get that true core of understanding of evolution. Okay. A couple of things, however, that I want to draw, because I want to actually talk about what evolution is and how it works and how an evolutionary biologist thinks about these things. Okay. And so what I want to do is I'm going to insert a slide, and I want to talk about two branches of evolution that you typically see in biology. One is called gradualism, and the other one is called punctuated equilibrium. Okay, so what is gradualism? So basically, what gradualism says is that species change gradually over time. Due to the accumulation of beneficial mutations. So mutation, you're mutating your DNA. So we're right where we want to be, right? We're thinking genetics as a function of this change. And so this is basically what the gradualists, how the gradualists see. Typically, what they don't really see is there is no fast change or catastrophe. So they didn't have a place for catastrophe. Okay. So here's a good example of a gradualist. So a gradualist, basically, a geologist kind of are gradualists by nature, right? So here's what they see. They see a mountain range being eroded away, like the Appalachians, right? Slowly over time at a very gradual, predictable rate, right? So that basically they're thinking the rates of erosion that we see today have always been in play and have never changed, right? And that the Appalachian Mountains are eroding at this rate over time. So you can extrapolate back and you could say at their birth, they were this high, okay? So that is a gradual type of approach. It's a slow, linear process. And you don't have evidence of catastrophe and change. Okay, that's how gradualists view things. And not only that, but typically when you look at an evolutionary biologist, right, they do what Darwin did, and they collect a bunch of organisms together. One of the things that they do when they try to understand their relationships is they build what's called a phylogeny. And all a phylogeny is a family tree. That's all it is. And so you have, what happens is a common ancestor, and the lines represent descent through time. And so you have some sort of a mutation that occurred in this descent through time. They note that with a hash mark, right? And so every time you get a new organism or a new species, it's due to a mutation, right? So if this line continues on like this, and let's say these guys continue on. Now let's say we have one that goes over here. That's a mutation that did that. There's a new mutation that created that new species branch. And then let's kind of do another one here. There's another one there that created that species branch. And then we're going to have another one over here. That's a mutation that created that species branch. So then what you get are all these little animals in real time. A, B, C, D, E, and F. And these are real animals. These are animals that we can collect here today, right? And so this is kind of how a gradualist sort of sees things, the slow accumulation of these mutations over time. And every time you get a mutation, that splits you off on the pathway to being a new species. Okay. Here's the problem with that, however. If you're going to be changing gradually over time, then you should see transitional species, right? You should see kind of something going from one species to the next as you're sort of evolving slowly over time. And so you should see an accumulation of these transitional species. The problem is in the fossil record, we don't see that. So we don't see what looks like transitional anything, actually. What we see are completely evolved species, like one and then two, and we don't see anything in between. So there's a complete lack of what's called, we refer to as the missing link. That's what they're talking about. The missing link isn't just a criticism of gradualism. It actually was a problem in gradualism because we would expect there to be a lot of transitional structures, a lot of transitional fossils. And we just didn't see it. And that was a problem, right? It's like it shouldn't be possible to have no record of these transitions. And so where are they? So that was a problem. The other problem was also catastrophe. In gradualism and in geology, they didn't really leave room for catastrophe. Everything was slow, like the eroding mountain, slowly over time, right? And so that was basically, or like the plateau that was slowly being carved out by the river, eventually over hundreds of millions of years becoming the Grand Canyon, right? So that was the idea, that everything was kind of slow and gradual, a slow descent, or if it's erosion or an ascent, right? That's very linear in nature. And if it's slow and linear like that, then you would expect to see transitional forms, right? But you didn't. And so there's a problem there with these two things, right? Okay. First of all, catastrophe, and this is one, so when I was at UC Davis, these two were at war with each other, gradualism and punctuated equilibrium. By the way, gradualism is the idea that was kind of mostly in place right after Darwin and through the most of that next 100 years, right? That was mostly what you had, was gradualism. Most of what you hear on these shows is some type of gradualism. And honestly, gradualism is good, but a lot of it is kind of old, dusty, antiquated 19th century thinking that is in desperate need of updating, right? And so the gradualists were very, very staunch. And when I was at UC Davis, it was a gradualist campus. And they were at war with punctuated equilibrium, which is actually from the Harvard School. And so they were at war. So I was like in the middle of the war between these two groups. And honestly, I had to be very quiet because I was kind of more of a punctuated equilibrium person, right? I would read their papers and it's like, you guys actually make more sense with what we see actually in nature in some cases, right? And here's how punctuated equilibrium comes around and what it actually is. Punctuated equilibrium is that essentially species change in episodes very rapidly. But most of the history, the Earth history, is in equilibrium. Let me explain this. So remember, the gradualists would say that the mutation rates were steady, right? The punctuated equilibrists would say that the mutation rates are episodic. The gradualists would say that catastrophe doesn't happen. The punctuated equilibrists would say that catastrophe drives evolution. It drives the species change, right? So here's how, so instead of like the slow, gradual incline of species change, the way a gradualist would see it, Here's how a punctuated equilibrist would see it. For the most part, you have these periods of equilibrium where there's no change. And then something would happen, some sort of a catastrophe. And then you get a very rapid change, speciation, until you hit another plateau where you have no change. And in these times of rapid change, this is basically where the mutation rates will increase very, very dramatically. So the rates of the mutations, the change of DNA is dramatic and very high, and the rate of species change is dramatic and very high. And so the punctuated equilibrist would basically say that for the most part, species development across the eons is mostly an equilibrium, no change, right? That's punctuated by episodes of catastrophe where the mutation rates accelerate and you get these rapid speciation events and mass extinction events, right? We're just now getting to the place where we're starting to feel comfortable with the concept of these massive extinction moments, right? So, but there's also massive evolution moments. So along with mass extinction comes mass evolution, right? That's what natural selection does. If you are fit, you live. If you're not, you die. We think of the die part, that's our mass extinction, but if you live, that's your evolution, right? So you get these punctuations of dramatic species change in an otherwise fairly equilibrated, no change history. So what does that mean? How does that help us? Well, first of all, that helps us to explain how nature is. Number one, it explains the fossil record problem. This is an explanation, and this is actually one of the driving reasons for punctuated equilibrium. This is an explanation for why we don't see transitional forms, is because in those moments of punctuation, when the mutation rates are high and the change rates are high, the animals are dying and evolving so quickly that they never have an opportunity to get deposited into the soils to become fossilized. As a result, they change so fast that they never actually get fossilized. So what we see are organisms, forms from one equilibrium level to the next equilibrium level. That's what we see. And that's because it's just going too fast for fossilization to catch up to it in those punctuated areas. Okay. The other thing that punctuated equilibrium does for biology is it basically syncs evolution to real life. Part of the problem with the gradualists is it requires you to ignore the actual realities of the planet, right? I mean, how can you sit here and say that there's no catastrophe when we know full well that the Earth has had a violent and catastrophic history, an exceptionally violent history? Catastrophe actually seems to be more the norm than the exception. And yet gradualism doesn't give credence to that, right? As a matter of fact, do you guys remember what killed the dinosaurs 65 million years ago? Right? We have that one on the exam. We all get an A on that one, don't we? Right? That's Chicxulub, right? That big meteor that hit right on the Yucatan Peninsula. But do you remember when that was first? Of course you don't, because you guys weren't even alive. Your parents probably weren't even alive. But I remember it. Not that old. But it was actually first proposed around the late 70s, early 80s. And I was little, but I remember actually the arguments. The gradualists pushed back on that meteor strike incredibly strongly. I mean, very strongly. They thought, they were like, no, you're a quack. A meteor did not, disappear the dinosaurs. Evolution of gradualism says that they basically went extinct slowly over time. A gradualist basically was pushing back on the possibility that dramatic catastrophe has the capacity to render all these species extinct because it is not in sync with that gradualist concept, right? Because a gradualist doesn't like catastrophe. And so that was a very controversial idea in its day. Now, it's not a problem, is it? Actually, if I were to tell you anything different, you'd probably look at me like I'm nuts, but it wasn't that way when it first came out. So that's kind of where the gradualists were, right? That just kind of gives you an idea of where that is. And so those are the two big fields of thought. And as we go through the chapter, I'll kind of come back and sort of add to this. This will be an ongoing conversation as we sort of touch on different areas, and we'll kind of talk a little bit about a combination of things like, what do we really know well and what do we not know so well, or, how does, is this idea a gradualist idea or is it a punctuated equilibrium idea, those sorts of things. And so we'll kind of take a look at where that evolutionary underpinning is for each of those particular ideas. But this is basically one of the things, the two different fields of evolution. I have a lot more to say about phylogeny itself. That is this little family tree over here. That's important because phylogenies are not as easy as they look. Okay? And we never say that out loud in evolutionary biology circles, right? But phylogenies are incredibly difficult to interpret sometimes and to really understand clearly. Talk about that a little later as we start talking more about relationships of things and how they're related to each other. Okay. So that's basically what we did with our diversity, right? That's basically what evolution is trying to do. It's taking current diversity, organisms that are still alive now, and then tries to get a sense of what their relationships are. And that's the reason why I take the time to talk about gradualism and punctuated equilibrium, because these are two conceptual frameworks that allows us to be able to interpret the relationships of organisms between each other. And they have very different interpretations depending on how you look at them, right? So that's the reason why I mentioned those two. The different thing I want to mention just quickly about phylogeny, and I'm going to build on this here throughout the semester, is when you start off building a phylogeny like this, is what evolutionary biologists do, right? They build a phylogeny so we understand how closely related or not organisms are. The thing to always understand about a phylogeny is the only things that actually exist on this tree are these guys down here. None of this up here exists. So a lot of it is hypothetical. Right. So a lot of times people don't realize now if possible, sometimes we get lucky, right? And we'll find like a fossil that we can say is going to be the common ancestor between C and D. So we can do something like that sometimes, but that's pretty rare. Most of the time when you see a phylogeny like that, the rest of the tree doesn't exist. It's mostly hypothetical based on how current organisms look to each other. Okay. So it's kind of like caveat of that problem. The reason why we know that's a problem is, let's imagine that you've got like a doppelganger, right? And you're totally unrelated, but when you take a look at the two of us, we look very similar to each other. And you would say, okay, you two, because you're very similar to each other, you must be closely related. So you have a common ancestor, similar parentage, right? The problem is that's actually not true, right? One of my favorite doppelganger pairings, because they're two individuals that I love, is Bono of U2 fame. That's my crew, right? So that's my group. And Robin Williams, who's my favorite comedian, was my favorite comedian, of course, right? If you take a look at the two of them back, especially in their younger days, like around 80s-ish or so, 90s, Robin Williams and Bono look kind of similar, right? Take a look at them. So if you use this idea, you would say, okay, Robin Williams and Bono are similar, and so that means they have a common ancestor. But they're like not anywhere closely related whatsoever. I mean, they basically grew up on completely opposite sides of the Atlantic Ocean, right? And so that's kind of what we're talking about, right? So there are some caveats to this process that we use to try to understand relationships. Okay? It's not as easy as we make it sound. And I think that's important, right? Because when you see a show say, oh, well, C and D shared a common ancestor, right? Because they always have a British accent on those, like, National Geographic shows for some reason. It's like, well, that's what your hypothesis is, but technically speaking, that common ancestor doesn't exist. So really, you have no clue who the common ancestor is of C and D. It could be C and D have absolutely nothing related to each other whatsoever, because you don't really know any of the rest of the stuff up there on the tree, right? And so that's kind of where some of that is, and it's a little dishonest to not lead with that, right? Because then what we do is we basically say stuff and we say, well, just trust me, that's the way it is. It's like, no, that's not the way it is, because if you're not being honest about what you do and don't know, you're being deceitful. That's the way I see it. Okay. And that's not okay, because what that all does is basically creates a lot of distrust with science and public. Okay, so here we have this diversity, right? And that's kind of the big theme in biology. There's a ton of stuff out there. And so how do we organize it, right? So basically what we're going to do is we want to organize it into groups. So we're going to first start off with, it's called taxonomy. Taxonomy is the organization of organisms by morphological similarity. So we just started organizing stuff, right? So we started putting things together, and that's kind of how we started doing this. So that's what taxonomy is. And as we started organizing things, we basically did kind of what's like a kind of a biological 20 questions, right? Any guys play 20 questions? Right? It's kind of like it's a good drunk game, right? Usually you're thinking of a person, right? And then you've got 20 questions to be able to figure out who you're thinking of, right? So oftentimes the first questions are pretty global, right? They're things like that can like eliminate half of your options, like right off the top, right? So let's imagine probably one of the most common first questions in 20 questions is going to be what? Yeah, right, male or female. Are you male or female? And if your answer is neither, then that just eliminated a whole chunk of your options. You just made it really easy then, right? So let's just stick with the traditional male-female thing, right? So what you did there was you basically eliminated 50% of your options, right? And then you kind of do that same thing. You have these binary questions, right? So, you know, are you famous? Yes or no, right? Yes, right? Are you an entertainer? Yes or no? It's like the answer is no. Okay. Famous person who's not an entertainer. Are you a politician? Right? And of course, that case, give you yes or no, right? So, well, yes, right? So you kind of notice how as you answer the questions, progressively you get closer and closer and closer to the individual that you're thinking of, right? And that's exactly what we did with taxonomy. The first question, the most inclusive one, basically kind of cuts a lot through it, is essentially what's called the domain question. And essentially what's going to happen is we start to process these guys into domains. Now, what I want to do is I'm going to explain what a domain is. The first level of taxonomy is the domain. This is the question we're asking. Is it a prokaryote or a eukaryote? So there's no reason why you should know what those are just yet. You will know shortly. But just to kind of be brief, right, a prokaryote, these are just basically the two different types of cells that you can see in the world. All cells basically will drop into one of these two categories, either prokaryotic or eukaryotic. So what defines them, right? How do we know the difference between the two? There's a short list, a three-step list. First of all, prokaryotes don't have a nucleus. Eukaryotes do. Prokaryotes have no membrane-bound organelles. Eukaryotes have lots. prokaryotes are also super tiny. Cells that are eukaryotes are pretty large. And so as a cell type, you're going to fall into one of these two categories, the prokaryotic or the eukaryotic. And that sets our first level of distinction in organisms. And we call that the domain level. Now, there are three domains. The two that are prokaryotic. So one is domain archaea. The other one is domain bacteria. So these are the prokaryotic ones. And then we have domain eukarya. So these are the eukaryotes. So then, from that domain, we've divided them into three domains. Now we want to ask the next question, right? And that kind of that divides it further into the next taxonomic level, which is kingdoms. And you can continue to go on with this, right? So the next one is phylum, class, order, family, genus, and species. And so you want to remember that in order. And the way you do that is by remembering this. Drunk kittens playing chase on freeways get smashed. Domain, kingdom, phylum, class, order, family, genus, species. Now, the kinds of questions you're answering at this particular point, you'll ask, like in one particular level, like for us personally, you'll ask a question, do you have a backbone or not, right? So if you do, you're part of what's called vertebrata. If you don't, you're invertebrata, right? So you're invertebrates versus vertebrates. So we're a vertebrate. Insects are invertebrates, right? Because they don't have a backbone. So that would separate us from the insects. And then like when you're talking about mammals, right? So you could talk about like, well, if you wanted to differentiate a mammal between a non-mammal, then you can ask this question, right? Do you have mammary glands and give live birth, right? And if you do have mammary glands, then that makes you as part of Mammalia, like that's us, right? And then if you don't, then you're something else, right? So like turtles, for instance, are egg layers, so they're not mammals. Monotremes, like platypus, which are a little confusing because they're a mammal. Why? Not because they have live birth, they lay eggs, which is weird for a mammal, but because they have mammary glands. So that makes them a mammal. So they're the one egg-laying mammal that's out there, the monotremes, right? So that's kind of how you're classifying that. Or like you can also classify it by what we eat, right? So like the difference between herbivores and carnivores, you're asking the question like, do you eat meat? Yes or no? Then you're carnivora. And do you eat grasses or vegetation? Then you're herbivora, right? So do you eat both? Then you're omnivora, right? So that's kind of where you get, so you can kind of see how you can differentiate depending on what you do or you don't have, right? Until eventually you get down to your genus and species, which together is referred to as the specific epithet. This is like your name tag. Now, under domain eukarya, we have 4 main kingdoms, and they're typically based on how they process and how they accrue energy. So for instance, over here you have kingdom Animalia. These guys are what's called the heterotrophs. What does that mean? That means we have to consume our food, right? Kingdom Plantae, these guys are autotrophs. What does that mean? That means they make their own food, right? And then you have kingdom Fungi. And these guys are different. So they basically absorb food from the external environment. So they kind of have what's called saprotrophy. I don't want to get too much into those because they get a little jargony, right? But they basically have a different strategy. So they don't make their own food. They don't really consume their food. They digest their food from the outside and they absorb the nutrients. So that's a little bit of a different version of that. That's the reason why they have their own kingdom. And then, of course, you have Kingdom Protista, which kind of has, it's kind of a bit of a miscellany, really. Mostly single-celled organisms. Some of them are colonial. Some of them are not. Like kelp, for instance, you can see the kelp is actually colonial algae. Algae is a protist. So they basically form large colonies that creates these big kelp fronds in the ocean. But protists tend to have either animal-like characteristics, heterotrophic, or plant-like characteristics, autotrophic. Okay, so they kind of have a little bit of both in there. So a good place to find protists is pond scum.
Would mushrooms be considered both because they can eat human flesh as well as they can live off the land?
So not really, because what they do, even regardless of what they're eating, they're doing an external digestion. So for instance, with heterotrophy, what you're doing is you have to internalize the food, bring it in where you digest it. Autotrophy, same thing, you're making your own food. With the fungi, what's happening is you externally digest the material and you absorb the nutrients.
So through the mycelium.
Yeah. Mm-hmm. Yeah, so it's and that's kind of like what's happening with like a rotting root or something like that under the ground, is the mycelium is basically secreting out all these digestive enzymes, breaking down the cellulose and all that sort of the nutrients and things like that, and it's absorbing those nutrients into the organism. But it would be the same thing with us, right? So it'd be breaking down our tissues and then it would be absorbing that into itself. So it's like external digestion with internal absorption. That makes sense. And that's kind of fairly common for all the fungi. So those are our kingdoms. And then eventually you get down to your specific epithet and you get to things like this. Maybe know what that is? Yeah, so this is your genus and this is your species. Now, one of the things to understand is, and I want to use the next 5 minutes, we'll take a break at noon. But I want to stop here to explain, it's kind of an evolutionary thing, a little bit of something that nobody really ever talks to you about. So when we take a look at species, that's what we're talking about in evolution, right? How do species change over time? So a core principle of understanding that is understanding what a species is in the first place, right? And here's the thing. What a lot of people don't know is that there's not a single definition for species. There's actually like a half dozen definitions for species. And depending on which definition of species you use, it will change your interpretations of your results, which is a problem. And nobody ever tells you that when they're talking about these are species are evolving over time. And it's like, okay, first of all, what definition of species are you using? And how are you defining that species? The most common definition that you see is what's called the biological definition. Basically, there's two pieces to that. A species is separate if they are both geographically or reproductively isolated from each other. That is to say, you can't interbreed. You can't hybridize with each other. Okay. But here's the thing. Let's muddy up this water, right? That sounds pretty easy enough, right? Like for instance, dogs can't hybridize with cats. They're two separate species, right? Giraffes can't hybridize with lions, right? They can't do that. They're separate species. That makes a lot of sense, right? But what if they're very close? For instance, let's take a look at this one. Anybody know what that one is? That's a wolf, right? Can Canis familiaris and Canis lupus hybridize? Yeah, they can. We've got the wolf hybrids out there to prove that, right? But here's the thing. Here are two different species, Familiaris and lupus. They've got their own species name. And yet they are in violation of the definition of a species. According to the definition of a species, the fact that these two can hybridize actually is telling us that they're probably not separate species really at all. Here's another example. How about bears? Anybody like bears? The great bears, the big ones, right? We've got three major ones actually in the US, don't we? So we've got polar, grizzly, and black, right? So Ursus americanus, which is black, Ursus horribilis, which is grizzly, and I think it's Ursus albicans for polar, right? Albicans being white, basically, for polar bears. And those are three separate species, right? They've got their own specific epithet identified. They've got geographic isolation, yes? But do they have reproductive isolation? Can those three bears hybridize to each other? They can. Because we actually have grizzly polar hybrids. They don't because they live in completely different habitats, right? But that would suggest that these bears are actually not separate species because they're not reproductively isolated. So you can see here, even though we're comfortable with working with these three populations of bears as though they are separate species, in reality, biologically, what that hybridization is saying is that they're not separate species at all, right? And that gets harder. So it's really muddly, right? And this is the problem that nobody ever talks about, because when you're talking about species change over time, evolution, it really kind of brings up a really big question. It's like, okay, wait a minute. First of all, how do you even know when you've got a new species in the first place? And not only that, but it's like a slow creep. It's like there's not like a magic moment where you ring a bell and say, okay, I'm here, I'm a new species, take me out of the oven, right? It's like this sort of slow morphing of change that's so slow that we're not likely going to see it, right? So it's just like all of a sudden on this end, it's like, oh, wait a minute, this is totally different than this. But when did that happen? It's been happening. Over time. But the thing is, if you can't understand with integrity what a species is and when something becomes a species or not and how to identify a species clearly, it's going to complicate and muddle your interpretations of how that species change is occurring over time. That makes sense? That's a huge problem when you're looking at evolutionary relationships, because you're assuming that speciation is straightforward and easy, and it's absolutely not. It's a muddled mess. But nobody ever tells you that, do they? Have you ever heard that before? That's because it's not easy to explain. National Geographic would probably take the entire hour trying to explain just speciation and all of its pitfalls and caveats. This is one of the reasons why we don't do anybody any service by not coming clean with some of the things that are like, yeah, we think this is it, but there's some serious caveats here. I mean, we don't really know. I mean, is a polar bear a separate species of a grizzly? We think it is. We give them a species name, but the bears can hybridize. So that tells me that genetically, because that's where we begin, right? That's what it's all about, genetics. That's how it's changing. Genetically, they're telling me that these guys aren't as different as they are. You can make an argument based on that data that actually the great bears are more like us. You know, different cultural ethnicities within a single species. So we can interbreed with each other from different ethnicities, right? Because we're the same species, but we're not different species, right? And so you can make an argument like that. That really there's only one great bear species, and there's kind of like different ethnicities, for lack of a better term, right? Of the great bears, right? You've got the brown bears and the non-brown bears, and they can interbreed with each other just fine because of this species. So you can see how it gets very difficult how you're sort of pulling all this together. By the way, whenever you're doing what's called, and phylogenetically, what this is called is lumping and splitting. So when you're putting two organisms together in one species, but they're just like two different forms of the same species, what that's called is lumping, right? And when you're splitting them, that's called splitting, right? So you're kind of putting in their own little area. And so this happens all the time. But you know what's happening? When you do that, is you're changing that little phylogenetic tree. So that little phylogenetic tree is changing all over the place. And so it's not stable. A lot of people don't realize that. They think those family trees are like set in stone. It's like they're not. They're really living. They're changing, morphing all the time. We see this a lot in ornithology, right? So if you're an ornithology person, a bird watcher, right? We actually see this. One of my favorite birds, when I went to UC Davis, it was called the rufous-sided coati. Beautiful bird. They're all over Denver. You can hear them. You see the bird feeders everywhere. Dark black bird, bright red eye, kind of a reddish side. And the ones we have here have white spots on their wings. The ones back east don't. And so when I learned them, it was the rufous-sided coati. But what they did was they split it into different species. So now what we have is a spotted coati here, spots on the back. And the easterns have the eastern coati. Did that bird change overnight? No, just the way we classified it phylogenetically, we changed that because we understood something a little bit more. Right? So that's kind of the problem with phylogeny. As we learn more, those constantly are changing and shifting. So if I was building a conceptual house, I would not build it on a phylogeny because it's shifting ground constantly. But the reason why I stop and say that is because this is something that's inherent in species, and species is something that nobody questions and that is highly, highly misrepresented in just general public education. It can get quite muddy, and it can lead us to believe that we know things better than we actually do, because we're still trying to grapple with this concept of species and that kind of messiness of species determination. So with that one, let's go ahead and take a break. Let's take about 10 minutes and then reconvene, and then we'll kind of continue forward and start. We've already gone through taxonomy, and we'll start moving through some of the other major themes in biology. Okay, let's dig back in, shall we? So the collective wisdom of all of that is the properties of life, even though they do share some physical properties with non-living things, is a little bit more complicated than all of that, and it shows descent, right? So that's kind of the whole concept that organisms are connected with this continuous line of descent. That is to say that our DNA comes from somewhere, right? So we basically inherit that DNA over generations. That's kind of the idea. So there's kind of like this long, kind of continuous line of descent. And it's very similar to the way it is with our families, right? So it's the same idea. So genetics and evolution actually have a lot of similarities to them. It's just that one is a larger time scale than the other. Okay. So let's take a look then at a really, really critical idea. So we've kind of talked a little bit about one of the major threads of the tapestry of biology. We want to talk about some of the other threads now, right? Some of the other colors. And this particular slide will basically set the pace and the tone for everything we do throughout the rest of the semester. Okay. So what's on this list is what I refer to as the big biological questions of life. Okay. So here's how it works. For living organisms, they have, all of us, regardless of what we are, they have a series of questions that they have to come up with solutions for. No, there's no getting around that one, right? And so every organism has to come up with a solution. Now, it doesn't matter what your solution is, right? If it works, great, right? So, but you have to come up with a solution. And so here's the thing. Let's go ahead and get this out of the way straight up. What is the purpose of a living organism? That's it, right? The entire purpose of life is simple: reproduction. So you can tell your philosophy professors that they're out of a job, right? That is the entire existence and the purpose for not just human beings as biological organisms, but every organism on the planet. You have one goal. That's it. For you, success biologically is reproduction. Now, once that is there, this is your bullseye. Then the question becomes, what do I need to do in order to reproduce? Right? Now, here's the deal. I don't care how you do it, when you do it, where you do it, but you have to reproduce, right? I don't care what you have to do to get there, but you have to reproduce. At the end of the day, if you reproduce, you're successful. You pass the exam, right? Now, if you think about that, how you get there is open-ended, means that basically you're going to have all kinds of ways of getting there, right? It's kind of like you've always heard about those engineering challenges where a group of engineering students has, like, they have to build a particular robot and it has to be able to do this, this, and this, and that's it. But how you build it, what you do to get there, we don't care. So you see all these kind of cool, like, weird contraptions that these engineering students make, and they're all very different, aren't they? That's exactly what's happening here. We've been given a task: reproduce. Go get there, go do that. So since how you get there is open-ended, then you're going to get a lot of variations of how to get there. That's exactly why we have so much diversity in life. Is every organism is coming up with a solution that's a little bit different than the next guy, because they're answering the question in the way they like to answer it. Okay. Now, here's the thing. It's not, there are some things that we all have to answer. And that's what these questions are, right? So these big biological questions of life are questions that we all have to come up with a solution for. We don't have a choice. Because if we don't, guess what's going to happen to us? We'll die, right? So it's kind of a little hard to reproduce if you're dead. So the first goal of reproduction is live, live first so that you can reproduce. And then, of course, that's easier said than done, isn't it? Right? Because if you take a look at nature, living isn't so easy, is it? I mean, especially when you factor in the idea that other things want to eat you, the weather wants to kill you and wants to freeze you on one hand and wants to burn you to a crisp on another, right? It wants to drown you. I mean, it's a perilous world out there. So in order to survive long enough to reproduce, you've got to have a plan, don't you? Right? These big biological questions of life are part of the core questions that all organisms have to answer. But the solution they come up with is completely up to them. Okay. So here's the first one, cellular organization. When you take a look in the next couple of slides, I'm going to move through quickly because I want to unpack it all here on this slide where they're all in one place, right? And so cellular organization, what is that? Well, it's what it says it is, right? Basically, it's creating an organized body. Organized and regulated tissues and organs and things like that, right? So you have to have cell organization. If you don't have organization, you're not going to be able to get a whole lot accomplished, are you? Think about an orchestra. An orchestra has to have organization, instrumental organization, doesn't it? That is to say that the violins have to be arranged with the violas, with the cellos, with the double basses, right? So you basically have an organization. The woodwinds have to be together, the flutes, the oboes, the piccolos, the bassoons, and so forth, right? The brass section has their own organization. And then you organize it further and regulate it further with a piece of music, which is telling each group when, where, how, and how loud to play at a particular moment in time. So with all of that organization and regulation, you're able to get something that is pleasing and pleasant to the ear. What happens if you lose that organization and that regulation? You get chaos and noise, right? It becomes unproductive, right? And so that's kind of the importance of cell organization. So if you're going to be an organism on this planet and you want to survive long enough to reproduce, you have to be organized. You have to be able to do work in an organized, rational manner. I want to skip down to number 3, homeostasis. This is an important one. What homeostasis is basically is the maintenance of internal conditions so that they create a norm, kind of a normal or constant environment. Is the environment constant? No, the environment is quite chaotic, isn't it? It's very polarizing, isn't it? It's going to freeze you in one season, it's going to burn you up in another season, and it's going to be kind of nice in the other two, right? Only the bugs like those seasons too, so the bugs will then chew you alive. And so there's always a problem, right? So the environment is not homeostatic. It's incredibly chaotic. However, you can't do business that way, right? You can't do biological business in the midst of chaos. In order to get something done that's meaningful, you have to have a sense of constancy or normalcy. And that's what homeostasis is. Like, for instance, for you pre-health students, you're going to get a heavy dose of homeostasis when you get an A&P. Because homeostasis is the name of the game when it comes to internal physiology. Now, think about it. We are basically a walking bag of chemical reactions, all of which are in homeostatic control. That is to say that there is a constant normalcy in our body. And that's intentional because our body has to have something normal, constant, so that it knows what to do. Think about your temperature. You have a core body temperature of 37 degrees C, yes? And that's constant. Guess what? If that starts to increase, what happens? You start to sweat, which is your body's evaporative cooling system. You basically bring that core body temperature back down to keep it into a homeostatic constant normal range. If you start to cool down, what does your body do? Yeah, your muscles, your skeletal muscles start to vibrate and shiver, convulsively contracting. Why? Because they're creating heat so that it'll increase your body temperature and bring your temperature back up. So notice with homeostasis, it's basically you're creating this sort of oscillating ebb and flow like a tide of peaking and troughing and peaking and troughing, and you stay in that homeostatic norm. Okay? So everything for the most part that you can measure with your blood, like when you do a chem panel, you go to the doctor, most all of that is under homeostatic control. There is a normal amount of calcium in your blood, a normal amount of glucose in your blood. You know how I know that that's homeostatically controlled, everything? Is because whenever you get your test results, what do you see your number, right? And then what do you see next to it in the next column? The range, right? The normal. You have the low and the high, and hopefully your number is somewhere in the middle. You know what that low and high is telling you? That's the homeostatic normal range. If it gets too low, your body is supposed to do regulatory mechanisms, which gets it back into normal range. If it gets too high, your body does a separate set of mechanisms that gets it back into normal range. Right? So that's homeostatic. You're creating internal constant conditions. Why? Because you need that sense of constancy in order to be able to organize your cells and do all the chemical reactions necessary for these cells to be able to organize themselves. Well, not only that, but guess what? If you're going to reproduce, you're going to have to organize your cells, but you're not just organizing your cells for kicks and grins, are you? Because the one thing you're going to need to reproduce is a body. Not just any body, right? But a reproductively capable body. So we all start off as a single cell, yes? And through multiple rounds of mitosis and a lot of cellular organization over the next 9 months, we turn into little diaper right there. Let me give him some arms there, right? We turn into a little baby. By the way, they don't come out with diapers. I'm just saying, right? You have to go get those. And those little newborn diapers, I mean, they're so cute. They're like little, they get big quick. Right? So that's basically a lot of cell organization, right? A lot of homeostasis going on in there so that you can build a body. So you're basically growing at that point. You're also developing at that point. That's basically, see how these all feed together? Growth and development is essentially cells organizing themselves into tissues, into organs, and into your body, your actual individual body. But guess what? Growth doesn't stop at birth, does it? When you're born, are you ready to have kids? Why not? You've got a body, don't you? We may have a body, but we're not ready, are we? We don't have a reproductively capable body yet. That doesn't happen until when? Yeah, puberty, right? So when our hormones kick in, right, estrogen for the girls and testosterone for the boys, basically that's when our sex cells, eggs and sperm start to get produced, and our body is basically saying, okay, we're ready to have kids now, right? That's basically when our bodies become reproductively capable. And so we have a lot of growing before then to do, don't we? We have to go from that little baby, and we have to grow up. A lot of our body is developing even at that age. Like our nervous system is developing. Our brain is really underdeveloped as a baby. Our lungs are underdeveloped as a baby as well. So a lot of those systems are developing. Our immune systems are developing. We're not quite ready to survive, right? So what we're doing is, this is minimal. This is minimal when we're at birth. We have a lot of extra stuff we have to pull together in order to make sure we live for a long period of time. You know why? For us, it's important. Do you know why? Like, why aren't we like a gazelle? You just drop and run, right? I mean, as soon as they hit the ground, it's like, okay, come on, you're not even dry yet. Just get on your feet and start running. Have you ever wondered why we're not like that? Because as a species, we have a different strategy, right? Instinct basically drives the survival capacity of a gazelle. And that little fawn, don't call it fawn if it's gazelle, but right, that little baby has all the instinct that they need in order to run from the predator, right? They're not as good as their mom or dad, but they're pretty good at it, right? For us, a newborn baby is just about useless. I mean, they're cute as all get out, but I mean, they have really not a lot going for them. They're just a bundle of reflexes. That's it, right? So they are for survivorship purposes. I mean, they're like top of the food chain. I mean, they're easy pickings, right? So how do we make sure that that baby successfully grows up and has babies of their own? That's up to us, isn't it, as parents? So we can't actually save our babies if we can't save ourselves, which is the reason why we have a lot of growth and development in those early years before our bodies become reproductively capable. The idea is that after about 12-ish or so years before puberty kicks in, you've had about a decade's worth of development and learning. And so now you might have a fighting chance of living long enough to actually raise a baby. Before that, forget it. You're all sitting ducks, right? So we have a different strategy. We can't just have kids and run. We actually have to live long enough to make sure those kids grow up to be surviving adults who can then have kids to have surviving adults, right? So it's multi-generational for us. This is one of the reasons why we have a development strategy like us, like we do, a long-term development strategy. Okay. But guess what? That's all part of our growth, isn't it? And as a matter of fact, a lot of folks would consider that. Now, we didn't used to think about this before. We used to think that you're developing in childhood, and then at puberty, you kind of do your last development, and then you stop growing at 18, and then you're an adult, and then that's basically the way you are until you fall apart and die when you're an old person, right? But now we don't really see it that way. We see actually that there's different developmental windows all throughout life, right? So you have your childhood window, you have your puberty window, your teenage window, you have your young adult window, you have your post-young adult window, right? Kind of where the midlife crisis sort of sets in, your 30s and 40s, things of that nature. And then you kind of have your post-midlife, that's kind of 50s-ish, 60s-ish, and then you have your geriatric developmental phase. And there's different developmental processes that are going on in each one of those that are kind of like a developmental thing in its own right. Your body is constantly shifting from one developmental plateau to another, right? You might have heard of the notorious metabolism shift in your 40s. That would be considered a development, like a movement from one developmental stage to another. Okay. Where like when we're in our 40s, we start to realize I can't really slide into second base the way I used to when I was 20, right? Without like going to an orthopedist. So that's kind of like, that basically is telling your body is shifting into a new developmental window, right? And so we see them now instead of just, you reach an apex and you just kind of fall apart from there on. We see it as more of like your body kind of like going through different shifts throughout your life. Okay. And we've known this for a long time, like with women, right? Because of menopause. And so there's a huge developmental shift there for women in menopause, but now we see it more as global, right? So it's not just women, it's men as well. So it's men and women that are going through different types of developmental shifts throughout life. But guess what? That's all part of these questions, right? Why do we want to live to be old? I mean, if you're 60 or so, you've had your kids, haven't you? Biologically speaking, you're wasting resources, aren't you? You're breathing valuable oxygen. You're eating valuable food. It would be better if we expunged you from the planet and save the resources for the young that are coming up. Have you ever noticed that a lot of animals, that sounds pretty drastic, right? That's not social commentary, but I'm trying to draw a parallel here, right? Because a lot of times if you notice that a lot of animals don't live to be old. There's no such thing as an old age animal like us, right? We're different in a lot of ways. For a lot of animals, as soon as they, for some of them, right, as soon as they have kids, they just crawl off somewhere and die. Their life expectancy after they reproduce is very short. Our life expectancy after we reproduce is very long. actually. In some cases, it's actually longer after reproduction than before reproduction. Like if we have kids when we're 20, hopefully we live until we're 90 or something like that, but we have a much longer life after reproduction than before. That's very different, right? We think of that as normal because we're in our own skin, but that's very different from what most animals are doing. The other thing also to remember is that part of the reason, not all the reason, but part of the reason why a lot of animals don't get old is because, let's face it, when you get older, you get slower. Ask any athlete, right? They know that. They can't run as fast in their 30s as they did when they're in their 20s. Any wide receiver will tell you that. Any cornerback will tell you that, right? But the same thing is true for everybody else, whether we're a football player or not. Now, what happens if you're a gazelle? Do you get to just sort of die peacefully in your bed with your family gathered around you? No. You know why? Because if you're getting slower, that means your predator can catch you and you're going to get eaten. So the outcome of most animals on this planet is not to die peacefully in their sleep or in a hospital or with their family around them or whatever. Most organisms on this planet die a violent death of basically being eaten, because that's what happens. You just get too slow, you can't run away from the predator anymore, and you get eaten. So in a lot of ways, we are very spoiled. So you should feel very grateful to be a human being and not say, for instance, a snowshoe hare, right? Who's at the top of everybody's menu, basically, if you're a carnivore. Okay, so that's all kind of part of the growth and development idea. And of course, that you need that in order to be able to reproduce, right? In order to be able to reproduce successfully, you have to have that body, that confident body that requires growth and development. But guess what? There's one we haven't covered, isn't there? What do you need in order, because nothing comes for free, right? What do you need in order to create the cellular organization? You need energy to do it, right? That doesn't just happen miraculously for no, out of thin air. You have to physically put them together. That takes energy to do that. What do you need in order to control your internal environment to actually make and create all of these different things that will kind of create this homeostatic oscillation? You need energy to do that. What do you need in order to grow and to develop? You need energy to do that. How do I know that? You know that? Two scenarios. First one is going to be development. I'm going to take a look at 0 to 9 month development. If you've ever been pregnant, now I haven't, just for the record, right? But if you've ever been pregnant or you've been around a pregnant person, like routine, like somebody in your family or something like that, where you see them from day to day, what happens to their appetite? Yeah, the appetite goes way, way up, doesn't it? Right? Heard the phrase, you're eating for two. That's not necessarily a nice phrase to say, like, well, you're eating for you and your baby, right? That's also a phrase that captures the increase in the amount that the woman is eating. Why? Because the energetic demands of development, of putting together a new little body inside of her is so energy demanding that it's triggering her, because mom does everything for the baby, right? Until the baby's born and can do it for themselves. But that's triggering her hunger response, because now she's having to eat enough energy in food to fuel the developmental process of her baby, as well as her own energetic demands of her own body. So she literally is consuming energy for two individuals, right? And so there's a lot of energy associated with that. Growth, another one for growth, that's a such period of growth. But here's another one. When you were a teenager, I remember this very distinctly. I mean, when I was a teenager, I was like a food tornado. I mean, I was a black hole for food. I mean, I would come through like a plague of locusts, and I would empty out the refrigerator, and then 5 minutes later, I would look for another refrigerator to empty out. And it was just like a nonstop cycle of just absolute voraciousness. Any hungry teenagers in the room? Right? Now, I wasn't that way when I was a kid. right? I mean, I wasn't a huge eater when I was a kid, and I'm not nearly like that now, right? But why was I then? I was on the tennis team, right? If you're athletic, it's even worse, right? So yeah, I mean, you literally can't like just give me. It's like constant. It's like you're eating in your sleep. It's like you're just give me like one of those like a drip cake or something like that. I just snore and just feed it directly into me. I mean, it's just it doesn't stop. But all teenagers, a lot of them, I'm gonna say all of them, have an increase in appetite as they hit those teenage years. That's different for different people. But the reason why, all gets back to energetic demand. If you're eating more energy, it means your body is demanding more energy. Why? Because during your teenage years, that is the period in your life where you experience the fastest growth of all your life. You're going from a little kid to a 6-foot monster, right? Now, of course, within reason. I never got there. By the way, that's all I wanted. I was not greedy. I just wanted 6 feet, just 6. I didn't get there. I 2 inches short. I mean, I was like really right there. I was like, I'm almost there. Right. So I didn't get it. So I'll go, oh well. But why? It's so during that period that you're growing very rapidly, right? And so different people will do that. Some people are kind of a little bit more gradual. Others, like, I mean, over a summer, it's like they boost up like 6 inches. I mean, and so it's very dramatic, but that extra growth is fueled and is required a lot of energy. So the faster you're growing, the more energy you're eating, which is the reason why teenagers tend to be voracious. And they tend to eat a lot. Notice where everything is coming down to. In order to do a lot of what you need to do to reproduce, guess what you have to have? It all comes down to energy. So oftentimes one of the very first and most fundamental questions that you have to answer as an organism is your energy strategy. Where are you going to get the energy from? How are you going to get the energy? Because let me tell you, every time you answer one of these questions, it basically sets up a series of consequences that will basically form constraints on what you will become as an organism. Here's an example. If I am a bacterium, I'm little, right? Microscopic. If I'm me, I'm big, macroscopic, huge. Why? Did I go through life and say, you know what, I want to be small. I'm going to be a single cell, kind of like going through McDonald's, right? So just give me the small cell, and I'm just going to, I always seem to lose energy for that to kind of feel that, right? That's kind of the way we think about it. We sort of talk about the structure first. And we say like, oh, well, you have this function, you have to do this structure. But that's not the right way to think about biology. What I want you to do is sort of turn that around. I want you to think about biology first with these big biological questions of life. So here's your answer. Here's your question. What's your energy plan? Answer it, right? So that's your answer. And so you have a couple of choices there, don't you? It's like, well, you know what? I want a really elaborate energy plan. I want to get one of those big power plant energy strategies that produces buckets of energy. That's what I want. I want a lot of energy. Okay, that's a possibility. Go ahead and do it. Or maybe you're like, you know what? I don't want to invest that heavily in the energy plan. I don't want all that. I just want a little bit of energy, right? So it's a little easier because then I can have maybe more resources to do other things with. So I don't want to get all in just yet. I don't want to push all the chips to the center of the table just yet on energy. So I want a more modest energy plan. Well, now you can do that. There's no problem there, because remember, the only requirement is for you to reproduce. But once you make that decision, guess what? There's consequences to that decision. So if you have the modest energy plan, then what that basically means is you're only going to have enough energy to produce a very small body, like a single cell. So the bacteria is a single cell, not because it chose to be a single cell, but because when it organized its energy plan, it only produced enough energy to afford a single-celled body. We are large and elaborate and complex because we chose differently. We chose to have the large, elaborate energy plan that produces buckets of energy. And so it's able to fuel a lot more structure than the single cell. So that's the reason, that's the way I want you to look at it, right? So as each cell hits one of these questions, and it comes up with a solution, the solution will constrain its realities. Okay? It's kind of like decision making, right? It's kind of like your reality. That is true, right? Reality basically is a jumble of consequences. Matter of fact, your reality, what you perceive as real in your life, good, bad, or indifferent, is basically the lump sum of all the consequences of all the decisions that you've made in your life up to this point. Right? So that basically is your reality. Now, and that also means that if you don't like your reality, then the person in the best position to change that is you. Right? So, because you're the only one who can make decisions for yourself, and the other people can make decisions for you as well, right? But you are in the best position to make those decisions that constrain your reality. Here's a good example. I don't have a Bentley, and I'll use the Bentley a couple of times throughout the semester, right? Why don't I have a Bentley? It's obvious, because I'm here, right? Now, I don't have a Bentley because I chose not to have a Bentley, right? I drive like an 18-year-old half rusted out Ford Escape. But it's not like I sat there and I was like, rusty Ford Escape, Bentley. You know, I'm gonna have to go with the Ford Escape. I mean, that rust, that's the selling feature right there for me, right? That's not the way it happened, but yet that's the way we oftentimes see biology happening. Here's how it really happened. When I was growing up, I was told to do what I love, which in some cases is a fool's errand. And so I was dumb enough to actually believe that, and I did it. And so here I am, a science nerd teaching science, which I enjoy. However, that also means that because I chose a discipline or a career with a relatively modest salary, that means all I can afford is a used, half rusted out Ford Escape. So my reality was constrained by the consequences of my decision. If I had wanted the Bentley, guess what I should have done? I should have decided for a more energy rich plan or a more money rich plan, right? And then I could have made a salary that could have supported a Bentley. But that choice that I made back then constrained my reality to what it is today. That makes sense? So, and that's kind of the way it is in biology. Every time you answer one of these big biological questions of life, your solution will constrain your reality. And so it pushes you down different pathways. And then, of course, once you reproduce, you're passing on your DNA to the next generation. And of course, across generation, then that leads to heredity, which is passing your traits on to the next generation. Okay. So cell organization, we talked about these guys. Energy utilization, those are the energetics chapters. Homeostasis, or this is just basically maintaining internal constant conditions, all of which require energy, right? Growth and development. It's a lot easier for a single cell organism to grow and develop, right? That's the one benefit of being small. Like when I was talking about, I want a more modest energy plan. Yeah, you only have a single cell, but what's the upside of that? You're simple, efficient, right? You don't have to put a lot of elaborate planning into your development because you're a single cell. So where I'm fueling away just like for months at a time as a little cell first, and then as an embryo and a fetus and a baby, I mean, I'm like spending almost a year trying to put it all together. Guess what? Guess how long it takes for a bacteria to reproduce? For an E. coli to reproduce at 37 degrees C, it takes 19 minutes. So what we do in 9 months takes bacteria to do in 19 minutes. That's a little bit of a pro on the side of the bacteria, isn't it? They can grow very quickly in a very short period of time. That's a limitation for us, right? We kind of take a lot of time to sort of incubate, if you will. Okay. But guess what? Doesn't matter. No. Does the bacteria reproduce? Success. Do we reproduce? Success. Doesn't matter in the end, does it? The differences between us creates diversity. And then of course you have heredity, which we'll be talking about in chapter 12 as well. Okay, now let's take a look at levels of organization. So when you take a look at hierarchical organization, this is basically kind of like the organization of all things, different levels that you have. The first level you're going to run into is called the atom, right? The atomic level. That is to basically say everything is made up of atoms. And we'll talk more about that in the next chapter, in chapter 2. And so atoms come together to form molecules. And these atoms are bound by chemical bonds. Like for instance, 2 hydrogens bound to an oxygen creates H2O, which we'll talk a lot about. And then molecules will form small molecules, and they'll form what's called macromolecules. I want to write those guys in here because we have a whole chapter on macromolecules. What is a macromolecule? It's a really big, complex, elaborate organization of molecules. There's 4 categories, right? We basically have lipids, carbohydrates, proteins, and nucleic acids. So those 4 groupings of macromolecules will come together and create organelles, which are basically structures with a defined function. Usually a big bio question, right? Like here's an example. Mitochondria is an organelle, and its function is the energy. It tackles the energy question of biology, right? So a lot of these big biological questions of life are divvied up between these organelles. And so if you have a group of organelles together, then it's basically a cell. So that creates the cell. Now the cell is what we call the basic unit of life. What does that mean? That means that this is the smallest that we can get. And still answer all the big biological questions of life. Beyond this, you can't. Like here's an example, right? I use mitochondria as an example, right? So what mitochondria does is works on the energy question. But mitochondria can't do anything for growth or development. It can't do anything for organization necessarily. It just focuses on energy. So in that case, if all you have is a mitochondria, it can only answer one question, but not all of them, right? So the cell is the smallest that you can get and still be able to answer all those big biological questions of life and have a complete, like a completely contained living system, okay? So you need all those questions answered. So this is kind of what it looks like in pictures. So you can see, you can have the atoms, basically everything's going to be made of atoms. Those will assemble through chemical bonds into molecules, which will assemble into larger macromolecules. So this is an example of DNA that they're showing you here. Those macromolecules will form the organs. This is actually an actual image of a mitochondria. So that's an electron micrograph of mitochondria. And then all those organelles taken together will form the cell. So this is a very specific cell, looks like a neuron that you see here. So that's an actual microscopic or micrographic image of a neuron itself. So that's a scanning, what's called a scanning electron micrograph. We'll talk about that more in chapter 2. So we're not done yet though, because now we just got to the cell. We got to keep going because there's more levels of organization here. By the way, I always like to do this for students. If you are typically in this area here, and you have a class that's focusing mostly at that level, usually you're probably in some sort of a chem class or biochem class. Okay. If you are in this area here, if your class focuses at that level right there, you're typically in a cell bio class, like this class here, right? So we focus a lot on that organelle cell level. However, what happens if we take a bunch of cells and put them together? Well, that creates then tissues. So a tissue is a collection of cells with a common function, and then multiple tissues will come together to form an organ. And then multiple organs will create an organ system. So if you're in a class that focuses on this, you're probably in an anatomy and physiology class or some sort of an animal anatomy class of that sort. So let me give you an example of how the organ system, organ, and tissue levels work. By using an organ that we all have, the liver, right? So the liver is actually part of the digestive system. It's actually one of the accessory organs of the digestive system. And the digestive system as a whole, its job is to digest, absorb, and eliminate nutrients, okay? Now, different parts of the digestive system works on different of those tasks, okay? And the liver is part of that system. And so that's a collection of organs. So in the organ system, you've got the stomach, the esophagus, the mouth, right? You have your small and large intestines. You have your colon, right? Your large intestines, that's the colon part. You have your rectum. And so you have your pancreas and your liver. Those are all members of the system. Different organs, same system, right? Digestion, absorption, elimination. Now the liver, as an organ, is composed of multiple tissues. So it doesn't just have one tissue in there because there's a lot of things going on in there. So first of all, the different tissue types that it has. And in anatomy and physiology, you actually learn this. Actually, my A&P class right now, we're going through that chapter right now. There's actually 4 basic tissues in the human body. There's what's called epithelial. There's connective tissue, right? And then a lot of us are familiar with connective tissue because of our joints. And then there's muscle tissue and nervous tissue. And those are the 4 tissues. Now, when you take a look at the liver, you have all of those in there. Why? Because you have the epithelial tissue, which is the actual liver cells themselves. Okay. Then you also have connective tissue in the liver because the different lobes of the liver are held together with little connective tissue membranes that holds them all together. So there's 2 different types of tissues. In addition to that, you also have nervous tissue because you have nerves that actually connect to the liver, which then communicate and coordinate the activities of the liver. So there's the 3rd type of tissue in the liver system as well. And then the muscle tissue. Okay, so maybe there's not so much muscle tissue but that's 3 tissues of the 4 that are in the liver itself. So you can see the liver itself is actually composed of a spectrum of tissues. And that's kind of where you get this organ definition. We have multiple tissues coming together for the common goal of what the liver needs to do. Okay. That makes sense? And so it's kind of what it looks like. So here's Denver's favorite mascot when we're not collecting them up and feeding them to the homeless, which is not a snarky comment. That's actually a statement of fact. If you guys don't remember that, Hancock actually did that a couple of years ago. Because of the uproar of all the geese cluttering up the parks and stuff like that. So they culled the flock And the plan was to actually feed them to the homeless people. And they did. So that's why there's not as many Canadian geese around as there used to be. True story. True story. Geese? Well, yeah, they're like any other game bird. Yeah, I mean, like if you're a game hunter, I mean, any of the fowl, right? So any members of the goose family, whether it's wild goose, Canadian goose, the duck family, I mean, they're all pretty similar. So just I always kind of thought that was a little sad, but because every time this year, I always like when I'm riding to campus, which is one of the reasons why I love riding in the summer, is you get to see the little goslings kind of come out. So you kind of get to see the little fluffy things kind of crawling all over the place on the trail. So it's always kind of nice to see them. Although this year I actually got beat up by a goose. So I could tell it was mating season for them because they get nasty during mating season. And I kid you not, I was like riding my bike. It was actually right over here. I was almost here. And I was like literally getting ready to come onto campus, and a goose was hissing at me. And I was riding my bike. I wasn't stopped. And it took off, and it like totally like just like clocked me in the head with his wing. I mean, like intentionally. It wasn't like, because you know how like they usually like go over your head, or he totally went right after me because he hit me like right here in the upper lip with the leading edge of his wing, which is like their little punching area, right? So he was totally coming after me. I'm all like, I'm riding my bike, for crying out loud. Just leave me alone. Yeah, I was rather proud of it actually. I got beat up by a Canadian goose. So one of the more pleasant moments of my summer so far. So that was kind of cool. Okay. So I was going to brush him off, but I didn't want to hurt him because I didn't want to like, make him miss the flight or push him into something that he'd crash into. So I just kind of braced myself and let him hit me. So just beware. Those hissing gooses, they mean business, right? But this is kind of what we're looking at. So here's tissue. This is nervous tissue. So here you have neurons, and you have glial cells, support cells, so different types of cells that are in the tissue proper. And that's going to go to form the brain, in this case, of the Canadian goose, which is an organ in the organ system, which is composed of brain, spinal cord, peripheral nerves, and things like that. So there's multiple components or multiple organs associated with this organ system. And of course, when you bundle the organ system together with other organ systems like the cardiovascular system, the endocrine system, and things of that nature, then you get the entire organism itself. Okay. So now let's keep going. We're not done yet, right? So we still have more organizational levels to get to. So now we're at the level of organism, right? That's basically a collection of organ systems that are all cooperating, working together. So we are an organism. But what happens if we get bigger than the organism? Well, that's basically where we move into population. So a population basically is a collection of organisms of the same species. So for instance, in this room, we have a population of Homo sapiens, right? Wait a minute, where's that population? Do you see any Homo sapiens? A trick question, isn't it? Yeah, we are the Homo sapiens, right? Yeah. So there's a population of Homo sapiens, that's us, right? Now then, what if we go another level up, right? What about community? This is basically where you have multiple populations interacting with each other. So for instance, there's multiple populations in this room, right? We have a population of tortoises. We have a population of guppies. We have a population of cockroaches, the hissing cockroaches, not scurrying around here, right? We have a population of millipedes, don't we? We probably also have a population of arachnids somewhere in the corners of this room. So multiple populations interacting with each other. By the way, this is the level at which we start to see a lot of those nature shows, right? Where you see predation, where the lion is attacking the zebra and taking him down. That's one population interacting with another population in a community, okay? Now then, when you move into ecosystem, this is basically where you have interacting populations, or excuse me, populations interacting. With themselves and their non-living environment. So what sets the ecosystem piece apart is the addition of the non-living environment. So this is us not just interacting with each other, predation, but also interacting with the non-living abiotic pieces like snow, rainfall, things like that. Okay. So that's an ecosystem. And then we have multiple ecosystems together. It's the biosphere, and the biosphere is better known as the Earth. Okay. Now, ecosystems are important because we're all trying to save them. Yes? We're trying to basically preserve species diversity. We're trying to protect our ecosystems. As a matter of fact, that was a big, big push behind the rampant, sort of ravenous logging of most of the 20th century, which I'm proud to say has largely become much, much more responsible in their tree harvesting than they used to be. I mean, it used to be there was only one strategy, that's clear cutting. And then they evolved into spot cutting. And now a lot of lumber companies are actually as aggressive in replanting forests as they are in cutting them down, because they realize that that's their commodity. And if they cut them all down, they're out of a job, right? Watch the Lorax, right? That's basically clear cutting at its worst, right? So basically then when you're looking, it's like back in the day, like when we were real, especially the rainforest, that's a tough one, right? Because we can control our own industry, our own logging industry. And that's the reason why the Pacific Northwest is in much better shape, say, for instance, in a lot of areas like the East, for instance, is because by the time the loggers got to the Pacific Northwest, we kind of imposed a lot of these regulations on them. So they can't just come in and wipe out our forests like they did with all the hardwood forests in the East Coast, which if you most of the East Coast was actually hardwood forest. A lot of people don't realize that. It didn't look like it does today. It looked like those old New Jersey hardwood forests, like all the way up and down the eastern seaboard. And so it's mostly devoid of forest now because we built all these big metropolises in that area and wiped pretty much everything out. And that was done before we were responsible enough to figure out what we were doing. The really hard one, and the really big hard one, like especially in the 80s, that was really hard for us, was the rainforest, right? Especially the Amazon rainforest, because we were starting to come into a sense that this was an ecosystem that was incredibly valuable, not just to Brazil, but to the entire globe, right? That, the Congo, those big tropical rainforest areas, because they had so much species diversity. And I mean, there's still stuff in those forests that we haven't even discovered yet. Some species in there that we're still like, whoa, what is this? Right? So, I mean, there's just so much going on in those forests, and they are so huge in terms of producing oxygen and scrubbing out CO2 in the atmosphere, that literally they're referred to as the lungs of the earth. And so it's difficult, right? Because now you have another country, Brazil, who's not quite as economically developed as the US. And here we are telling them not to cut down their forests. That's kind of a tricky one. It was public relations and kind of a foreign relations difficulty. But there was a lot of scream because the Brazilians were just clear cutting Amazon rainforest, just like, I mean, just at a bewildering rate. And it was very concerning. And so the entire global community kind of started to organize together and put pressure on Brazil. So I think Brazil is now better. They're not quite perfect, but they're better at trying to preserve the rainforest. But here was one of the big questions that I want to get to. Here's the big question. Imagine I'm a conservationist. And I say, we need to protect the ecosystems. So let's write up a bunch of laws, you politicians, so that we can protect these ecosystems, right? No killing any individuals, no clear cutting, nothing like that, right? You don't touch anything, you leave everything as it was when you found it, right? So we want very strict laws that you can't alter, touch, or malign any of these ecosystems, because if we do, we're going to lose species diversity, and we don't know if we lose that critical species, it's going to basically mean the doom of the ecosystem or our own doom as well, right? So now here we are, the concerned politician, right? And we're thinking, okay, fine. How big is an ecosystem? How much are you talking about, right? How much do you want me to set aside and protect? 10 acres, 20 acres, 90 acres, right? That was the question that Brazil was pushing back on. It's like, okay, fine, you want us to preserve the rainforest. So how much of it do you need, right? And so that was a question we didn't know the answer to back in the 80s. And it actually spawned a big research project called the Minimum Critical Size Experiment, which was a study of ecosystems to try to answer that question, right? What is the minimum critical size of an ecosystem in order for that ecosystem to function and to stay healthy? You know what the answer was? Pick a size. Yeah, it depends. We have ecosystems like the Amazon rainforest that require a lot of range in order to be functional. But what we noticed from this experiment is we also have viable ecosystems that are no bigger than the back of a beetle's shell. You have micro ecosystems in soil that could fill a thimble. And that's a fully outfitted ecosystem. That's not helpful for the politician, is it? It's like, okay, so I'll give you a thimbleful. There it is. Don't touch the thimble. Got it. Go ahead and clear cut the Amazon. Just don't touch the thimble. Right? So it kind of depends. And so that kind of is why it was tricky. So you kind of have to basically answer that question for each individual ecosystem. And so ecosystems can be very big or very small. Okay. So as you move into these different levels, it's kind of like leveling up in a game, gamers, right? You kind of get a new batch of powers, right? And that's kind of what happens every time you level into one of these. So here's our population. You can see you got a population of different geese here, composed of species. So here's a population of Canadian geese. Here's a population of golden eyes. Then those populations will interact with each other and form the community. Now notice what's happening here with this community. You have multiple populations. So let me go ahead and write those out. So here you can, it looks like you have some snow geese right here. So those are little white ones. That's one population. You have some Canadian geese. So there's a Canadian goose right there. The darker ones are the Canadian geese. You also have looks like a couple of other birds in there. Can't really see them too clearly, but it looks like some little sand plovers or those sorts of things right there. So little shorebirds that kind of skitter along the banks of this particular lake. That's another population. But notice, it's not just all about animals, is it? There's a population of grasses, a population of shrubs, a population of trees. All those populations are coming together to form this particular community of this little lake. And then when you add the ecosystem, notice you have multiple populations interacting with each other and also with their abiotic environment. Okay, so what are we looking at here? Nice mountain range, but where is it, right? How does this illustrate an ecosystem? Simple. Let's break it down. Where's the populations? You have a population of brush right here, population of fish inside the river, or the lake in this case. You also have, by the way, not just the population of fish, but you have the population of all those like little critters skittering along the surface of the lake. Those guys are also populations. You have the populations of the bacteria that are inside the lake that you can't even see. You have the population of the grass that's on the opposite bank, this population of this little shrubby bush of the conifers that are here. So those are multiple populations interacting with each other. So far, it sounds like a community, yes? When does it become an ecosystem? What they're trying to show you is this up here. And there's a dividing line right there. Anybody who's hiked up by the divide knows what I'm looking at right there, right? That's tree line. Right? That's the point at which the trees don't grow anymore. Why? Not because of they're interacting with ever living things, it's because of their interactions with the non-living stuff. That is to say that the soil up in this area is too rocky to sustain a root system, which is the reason why the trees don't grow there. That's abiotic, that's ecosystem issues. Not only that, but notice a lot of your water up at this level is also bound up in ice, not in liquid water. Roots can't suck up ice. They can only soak up liquid water. Guess what? That's another interaction with your non-living environment. Your water is bound up in ice, not in liquid form. That's the reason why trees don't grow there. So these little non-living parameters up there is what's creating this interaction. That's the ecosystem component. Okay? And then, of course, you have multiple ecosystems together. You create the Earth itself. Okay. So let's talk a little bit about some of the, and what I want to do is because we talked a lot about organization of different types of things, especially diversity, right? We've been largely mostly talking about diversity up to this point and how we organize it, how we classify it, and that sort of stuff. But what I want to do now is I want to kind of switch now to, it's kind of a little bit of a break point in the chapter, kind of shifting gears to now more of like science itself, right, as a discipline. What it is, and more importantly, what it's not. Okay, so basically, I want to look at kind of some of the philosophical peculiarities of science and how it's structured. Because when we go through life, we have to sort of operate in what I refer to as different or separate intellectual disciplines. And each of the intellectual disciplines have kind of their own sort of jurisdiction, if you will. Okay. Science has its own. But science is very, very different than like what most intellectual pursuits are like. I mean, we know that, right? Because a lot of times if you take a non-major student, I mean, maybe they're into financing or if they're into poetry or journalism or something like that. And then they get into science class and they're like, oh my gosh, I'm just not used to thinking this way, right? Because there's a way of thinking in science. It's very unique to science, but it also makes science very powerful for what it can do. Science is designed very specifically in one very specific way to answer problems. Okay. And we want to make sure we understand that. So let's take a look at science as kind of a philosophical organization, as a tool to solve problems. The first thing about science to understand is that science is focused on understanding the natural world. So basically, its focus is on natural law. The laws of nature. Okay, how do they work and how did we get here? That's basically it. It's focused on the natural outcomes of these laws. And as a result, it also focuses its strategy on collecting that information through observation and reasoning. Right? So it's a very kind of a deductive and logical type of a process. So those are critical pieces of science. This basically what this does is it defines your scope of inspection, right? So you're looking at natural phenomena and trying to understand at a very mechanistic level what that and how that works, right? And so it also requires reasoning. And what that basically means is you can't just, reasoning is the antithesis of the 21st century. Why? Because the 21st century is fueled by irrationality and unreasonable claims. The entire concept of social media is swallowed up in irrational, unreasoned, basically shout outs, right? I mean, you basically have anybody and their brother's uncle shooting out any kind of a claim they want with absolutely no rationale or reasoning behind it, other than the fact that they just opened their mouth, right? Science is the complete opposite. Science is like, keep your mouth shut unless you actually have a well-observed documentation, that's a type of data, a well-reasoned argument. Right? So you can see then that science has already done a couple of things. Number one, it's basically limited its focus to natural law, and it's also limited its discourse to data-driven reasoning, not opinion. That makes sense? Science is not interested in opinions, only in reasoning and conclusion, which is one of the reasons why it's difficult to think about scientific. Yeah. Well, there's a lot of opinion in dinosaurs, but even then, there's some reasoning behind how you got to that. So there's a justification to that. But it's still a part of the reasoning piece, right? So I'm thinking more of like opinion as like, oh, well, this is so, and then you don't say anything. Like, it's like, okay, how do you know that? You just want me to believe it because you said it, because you made that claim? That's what I'm talking about. With science, the idea is you'll make those types of claims, but you have to justify them with a reasoning, rational explanation. Like, this is my opinion of dinosaurs, and this is how I got there, right? That's what science does. In most of the 21st century, what you get is, this is my opinion of dinosaurs, and then you get nothing about how you got there and whether or not that's reasonable or rational or anything like that. That makes sense? So that's kind of the difference between science and just pulp mouth shots out there, right? So, and the reason why I say that is because the 21st century, we ask the public to think scientifically, but the actual trends of the public are going the complete opposite direction. Okay. So a couple of things also that I want to focus on, but I want to take some time to focus on them. So I'm going to probably stop at this slide and start with this slide. Is I want to kind of bracket these two concepts right here. And I want to clear some things up. I'm going to go back into sort of gradualism and that kind of idea of the rate of deposition, catastrophe, and stuff like that. But I've got a couple of examples of kind of the rationale behind the explanation of these. So kind of keeping with that observation and reasoning concept. Okay. But it's going to take a little while to unpack, and we're pretty much at our witching hour. So I want to leave it there. What I want to do is I'm going to start with this one. Sound good?